now it's completely empty.
Yes.
Okay. This is what physics says. Physics predicts this, okay? And experiment confirms. That the rate at which the water depth changes for the tube and the cylinder that we've used, the rate at which water depth changes is a constant multiple of the square root of the depth. There's a fairly simple connection in physics, but it kind of requires energy conservation and stuff, so I'm not even going to teach you the physics, okay? But that's the way it is, okay? So you accept that, and you accept that it's been experimentally confirmed to great precision, okay? Okay. This says a constant multiple of the square root of the depth is some number k times the square root of y, assuming y is the depth, and that's the way we've been using it, right? And y prime stands for the rate, okay? So y prime or dy over dt, that's like the change in y divided by the change in t, right? Is the rate. So this is saying the rate is some k times the square root of y. The k is constant. Okay? And if this is true, it follows that y has to be a quadratic function of t. And this is easy to prove. If you know one semester of calculus, I could run you through it. If you know 2 semesters, it becomes a pretty straightforward problem, okay? Especially if your course includes a little short introduction to differential equations. But it's very simple, okay? Not trivial. It's pretty good if you can do it. Okay, a lot of people can. Your typical A student, even a strong B student in a calculus class can easily do this. So it's not far from where you are right now, depending on how far you are from a calculus course, okay? So this can be proven, but we're going to kind of establish it anyway. So we're just going to see maybe what this means. Now, I'm going to say if y equals at squared plus bt plus c, I'm making an assertion here. We're not going to prove it, but we have spent the time and we've made it very plausible. I say on any interval centered at some x mid, at x equals some x mid, and I said x, and actually it should be t, because I'm using t for my variable, right? So let's kind of fix that. T equals t mid, and we'll call this t mid. Okay? Centered at t equals t mid, the average slope is 2at plus b. Now, that should be 2a times t mid plus b. Okay? If you've had calculus, you recognize 2at plus b is a derivative of at squared plus bt plus c. It's the simplest rule in calculus, and you know that within a couple of weeks of starting the course, depending how much time you spend on limits. And it's good to spend time on limits. Okay. So we're just going to check this out. We're not going to try to prove it in general, although we could. We're just not going to because it takes time, and you're probably going to get something like that in your homework eventually. Okay? And I'll break it down for you when I do. So we're going to let y equal 0.01 t squared minus 2t plus 140. Looks a lot like the depth versus time models you've been getting. Okay? Numbers here are like 0.0 something times t squared. Numbers here are, in the range of 2 or 3, whatever. And that's a number, around 100, whatever. Okay. And we're going to let t mid be 60. So what we want is we want t mid to be in the middle of an interval. so we can verify this statement, because this statement is talking about intervals centered at some t mid. So we want to look at intervals centered at 60. Okay, what are intervals centered at 60? Oh, 59, 61, 50, 70, 40, 80. So we start with 2100. Okay, just pick that for reasons that we can cut it in half and then cut that in half easily. Okay? So we start with the interval 2100, and we had a lot of discussion. How'd you get that? How'd you get that? I calculated the average rate of change of this function on this interval, which means that I calculated the coordinates of the point on a graph that would go with t equals 20 and with t equals 100, and I calculated the slope between those points. You don't have to look at this and say, where'd that point 8 come from? You can do it, right? Now, I made a big deal of that. Don't get hung up on where did that come from, where did that come from, when it's something that you know how to do. Okay? Just do it. You'll see where it came from. Okay? That's kind of an important lesson, because it's easy when you're studying mathematics to get tied up in the details. The book has an example. Where'd that number come from? What's the book doing? Do it yourself, then look at their numbers, or then look at their symbols. Okay? You'll probably get it. And you'll probably get better and better at it. Just advice. Okay, so 2100. So y changes from 104 to 40. How did I get 104 and 40? I did what I just said. And we get the slope, rise over run, is negative 0.8. You know how to do that. So I'm not going to explain it. Okay? Except to say that, okay, if t equals 20, then plug into this, you find that you have the point 2104 on your graph. And if t equals 100, that corresponds to the point 140, which is a little hard to read there, but that's what it is. So that's why y changes from 104 to 40. You can do that. You don't need me to tell you where it came from. But I understand why you'd ask. I'm not putting you down for asking. I'm just kind of giving you advice on how to approach stuff. Okay, so anyhow, we do the rise over the run. You know how to do that. We get negative 0.8, right? Okay, then we do the same thing on the interval 40-80, which is also centered at 60, because we're choosing intervals that are centered at 60. So on 40-80, we do the same thing, and the slope is negative 0.8. On 50-70, we do the same thing. The slope is negative 0.8. You could do 59 to 61, and the slope would be negative 0.8. It's always negative 0.8 if the interval is centered at 60. Okay? Okay. So, then I had you do a couple of examples yourself. Find the slope on 1050 and 2040. Everybody found that the slope was negative 1.4. And the slope of the green line, which should be labeled above, but I don't have room, is negative 1.4. Same slope on this line as this one, because they're both calculated on intervals centered at t equals 30. Right? Okay, so yeah, it's a big deal. We took quite a bit of time on it, but it's a big deal, so you really want to lock it in. Now, I have an algorithm for calculating this, although it's really pretty obvious. How do you calculate the slope on an interval? Well, you find y at each endpoint of the interval. Then you plot the points, which is optional, because you can find the slope whether you've actually plotted them or not, but it's a good idea to plot them because it reinforces what you're doing. You got a visual picture of what you're doing, not just numbers on a piece of paper. You got a picture. Then you want to reinforce that until you're sure it's never going to go away. And then, in parentheses again, you could compare to 2a t mid plus b, and you probably ought to do that. But 2a t mid plus b for t mid equals 30, which is what t mid is for these intervals. Well, a and b are the coefficients of t squared and t in your quadratic function, so a is 0.01, b is negative 2, right? So we put in 0.01 for A, -2 for B, and what do we get? We get -1.4. So I can write that down, 2 times 0.01 times 30 plus B, which is -2, is -1.4, which agrees with this and this. And we could easily write some symbols down and prove that it's always so. Probably won't want to take the time to do that because we have another focus here, and that's something you're going to learn to do pretty well anyway. Okay? Okay, well, now I just drew this trapezoidal graph up to the orange, okay? And I didn't label the slopes. I just labeled these and said calculate the slopes. Everybody calculated slopes and everybody got these numbers, okay? And that's for this function. So what happens to these numbers as you go from one interval to the next? Well, the slope always goes down by, well, slope goes up by 0.2. Slope is negative, but it increases by 0.2, doesn't it? So it goes from -1.9 to -1.7 to -1.5. We can conjecture that the next one on an interval of 10, because all these intervals are intervals of 10, right? If it didn't have uniform intervals, this wouldn't come out uniform, okay? That we get that the next slope would be -1.3, and that slope, if we extend for a run of 10, is going to give us a rise of -13. Okay, and we write that out as slope -1.3 for run 10 units to t equals 40. We get rise over run -1.3, so the rise over 10, because the run is 10, is -1.3. And you solve that for the rise, very complicated, you get -13, right? Not complicated at all, okay? Which means then that this value should go down 13 to give you 76. Now if you plug 40 into this function, that's exactly what you get. Okay? Because this pattern is valid. One thing I didn't say, and this is a big deal, so for any quadratic function, on a series of equal consecutive intervals, I don't have room to write it out. I should say the slope from one interval to the next will always change by the same amount. I'm not going to say the one interval to the next. I'll just say by the same amount. We're going to make this a little more specific, either in a homework problem or in something we talk about. Okay? Make sense?
Mm-hmm.
And that's illustrated here. Yep. I'll get out of it. I don't want you to break your phone. Okay. Okay, now, for the numbers that we've gotten here, we see that our midpoint slopes are -1.9, -1.7, -1.5, -1.3. Because those are the slopes and the intervals from 0 to 10, 10 to 20, and so forth. The midpoints are 5, 15, 25, and 35. And the actual slope at the midpoint is equal to the average slope in the interval. Okay? Now, we calculate y mid based on the trapezoid, not based on the actual function. We should have used the actual function. We fudged a little bit and just averaged the two y values we had on our trapezoidal graph. And then we did the square root of y mid, and amazingly, I estimated all those correctly to the nearest tenth. And then we evaluate k. Now what's k? Y prime equals k square root of y, right?
Mm-hmm.
That's why we calculated the square root of y min and the y prime at y mid, which is the midpoint slope. So then we get these values for k, and we find out they're not totally consistent, okay? And they really should be, but we're using a fairly wide interval, and the approximation kind of is going to kind of asymptotically approach something, I think. I'm not sure about that. Okay, anyhow, if we'd have used accurate values of y mid and all that stuff, and I'm not sure about my division there, it's close, but maybe not right. Okay, so now we have k equals negative 0.15, and we're going to use delta t equals 10, okay? And we're going to see what our rule is, if our rule is that y prime equals k square root of y. And we're going to see what numbers we get if we use this rule with an assumption, okay? So we start out with y equals 140. K is negative 0.15, y is 140. We calculate this, we get y prime equals negative 1.77. What's y prime? Y prime is the rate at which y changes with respect to t. That's the slope of our graph. If we follow a slope of negative 1.77 for 10 units, we're going to go down 17.7. In other words, our change in y will be negative 17.7. Okay? Then, if we add that change to the original y, we're adding negative 17.7 to 140. We get 140 plus negative 17.7, 122.3. Okay? So now, that's our predicted value of y. Now, I don't have the graph up there, but the actual value of y for this function at t equals 10 is 121. So we're off by a little, right? And why are we off? Well, we're off because...
Estimated values, most likely.
Yeah, because we kept the value of y prime constant. As soon as y starts to change, y prime is going to change. So we're not going to have the same value of y prime for the whole interval. Y prime, by the end of the interval, is going to be negative 1.7, if you remember where that came from, right? It's right there in the graph, okay? So we're actually, we actually have an error in our approximation, okay? Won't go into much more than that, because tomorrow we're probably going to go to a spreadsheet and we're going to use a smaller interval and we're going to see that things start agreeing really well. Okay, anyhow, there's our scheme. We take our 122.3, recalculate y prime, at, for y equal 122.3, get our delta y, add that, and now it's just boom, 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 and you can do it without even understanding what you're doing. But you should understand what you're doing. You should understand at every step, okay, I'm calculating the slope of this thing, I'm calculating the rate of change, so I know the slope and I know the run, so I can find the rise. I know the rate of change and I know how much t changes, so I multiply that by the rate of change, I find how much it changes, okay? You want to understand all those things. Okay, so that's where we are. Now, there are different rules, and I'm going to give you some different rules on your homework, okay? The rule here is k square root of y with k equals negative 1.15, okay? So you're going to have a starting value, you're going to have a rule for your rate, and you're going to have a delta t. Exactly as you have here, except your rule is going to be different, okay? So one rule y prime equals ky instead of k square root of y. Okay? Now, one thing about this. This rule gives you a quadratic function, which is just a transformed power function. X equals 2 power. Okay? Second power. This always gives you an exponential. could have y prime equals k. That would give you a linear function. And you have other examples of y primes. The only difference in your calculation scheme is how you calculate y prime. Everything else in the scheme is identical. I mean, you have different numbers, but the whole scheme is the same, because all the scheme is saying is that, okay, we calculate the rate of change of y, we multiply that by the change in t to get how much y changes, and we add that to our value of y to get a new value of y, which now becomes our value of y, and so forth. Does that make sense? That will have to beat your head against it for a while. It's not hard. But conceptually, understanding why you do every step is a little more challenging than just doing it. Just doing it is pretty simple. You know, you've already done this. If you've done this, you can do it for anything. Okay? Understanding what your results are and understanding why they are what they are, there's the depth to it, and we can only do so much with that. In this course, we've only got 3 class days left. Long days, but okay. So that's something you can look forward to.